Okay, so now we have known that the problem in general depends on time. In many cases, many for us, many times will say that the problem is quasi-static, so we can just neglect time as an integration domain. Well, let's now focus on another issue. How we solve, now that we have the equations, we have as many equations as unknowns, so theoretically we are able to solve the mechanical problem. The point is, well, you are able to, but how do you do that? How do you solve the problem? Well, we can do that by numerical methods, but before, it's very convenient to be acquainted of the ways at which this problem has been traditionally solved analytically. Of course, there is a limited number of cases in which the problem can be solved analytically, because the complexity of the equations in general doesn't allow resolving the problem analytically. But in a limited number of cases, and by the way, that's what we will do at this course. We'll solve all problems analytically. Of course, a selected number of problems which can admit some simplification and so on. But we are going to solve the problems analytically, because this is not a course on numerical methods, okay? So there are two ways of solving the problem, and they differ on what they consider the primary unknown. There is the displacement formulation, in which the main unknown, that's what you have to keep in mind, the main unknown are the strains. So we say, if we know the displacements, the main unknown are displacements. So the method says, I want to solve displacements, and then if I know displacements, I will know strains by differentiation, and then if I know strains, I will obtain stresses by applying the constitutive equation, okay? So I have to end up with a formulation or with a set of partial differential equations which are simplified with respect to original one, with respect to that original one, simplified because this involves 15 unknowns and 15 equations. This cannot be solved analytically. We have to simplify that. And we simplify that in such a way that we end up with a certain equation, partial differential equation, where the main unknown is the displacements, okay? And the other alternative is to use the so-called stress formulation. This is, I would say, nowadays it's just educational. Educational because it's a way to show you how engineers have traditionally used some smart solutions to solve complex problems, are the elasticity problems were. Nowadays, with the numerical methods, I just anticipate that the method that is mostly 99% of times used is the displacement formulation. Anyway, we are going to examine both of it. So, let's see what displacement formulation consists of. Look, these are the equations of the problem, right? We have the 15 equations, the boundary conditions in space, and the boundary conditions in time. Okay, we cannot handle 15 partial differential equations to solve it analytically. We have to simplify that. What is the way to simplify that? I'll tell you the concept. Look, if I introduce these stresses into here, and I obtain that equation, now, since the stresses are replaced by that, at the left-hand side, I would have just the strains. So I would have the Cauchy's equation just expressed in strains, okay? But now, if I introduce in the strains the equation of the kinematic compatibility of the strains with displacements, then I would have a unique equation, 3 equations, in terms of the strains which are replaced, in terms of the stresses that are replaced in terms of the strains, and the strains are replaced in terms of the displacements. So finally, this equation, the Cauchy equation, will be a set of 3 equations with just 3 unknowns, which will be the displacements. So that is the job. How to transform these equations and make them just written in terms of the displacements. That is what is written here, right? First, we just replace that equation into here. So we have to compute the divergence of sigma, which in turn is the divergence of lambda trace of epsilon times 1 plus 2 mu epsilon. We do that here. Okay? That is what we have here. So now this is the Cauchy's equation expressed in terms of the strains. Okay? And now we are going to replace into here the expression, the strains are the symmetric gradient of the displacements. So we do that. If now I consider that term here, for instance, and that term here, I replace in the strains the displacements after same operations, I found out that the divergence of the trace of epsilon times 1, at the end of the day, that's an operation that can be done in initial form, and you can check it. So finally, it can be obtained as the gradient of the divergence of u. So now we have that term here expressed as the gradient of the divergence of u. Okay? Which is that. Look that this term here involves gradient of the divergence. So second derivatives. That is the price that we are going to pay. This was an equation with first derivatives, and now after replacement, it's going to be an equation with second derivatives. So we increase the order of the partial differential equation. Okay, but we are going to have much less equations. So now we have to replace that also here. So we have to replace that term here. And again, replace into here the strains in terms of the displacements. And after same operations, I'm not going to detail it, we obtain that this term, the divergence of the strains, can be expressed as 1/2 of the gradient of the divergence of u plus 1/2 of nabla square, the Laplacian. You know, the Laplacian is nabla square of the displacement. So this is an analytical job, and at the end of this, we obtain something. We obtain that these original equations in terms of the stresses, after replacing the constitutive equation here, and after replacing the geometric equation in here, after everything, we obtain these equations here. These equations here. We have here the equations in compact form, and we have here the equations in initial form. Okay? Look, I want to emphasize that these are still the original equations. So these are still the second Newton's law. Force, you know, here, the force is still here. The acceleration is still here. So what is all that? Well, all that was just the translation of the original forces, divergence of the stresses that we already know, that are the counterpart of the tractions on the boundary at local point. So all this, finally, gives rise to all these maybe complex equations. You know, that's the initial equation. You know, here we are using, for the first time, the notation comma ji. What does that mean? Differentiation with respect to something. So that is lambda plus mu, second derivative of uj with respect to xj, xi. And that, for instance, is second derivative of ui with respect to xj, xj, xj. So twice, and by the way, here the Einstein notation about index repetition applies. So finally, these are three differential equations. And how many unknowns are there here? The displacements. So only 3 unknowns. So look, we have passed from a system that initially had 15 differential equations, differential and algebraic. This is differential, this is differential, this is algebraic, right? We have passed from this system which involve a large number of unknowns, by doing some mathematical operations. That is what our antecessors, our engineers before computers did. They solved this second order partial differential equation on the displacements, the three components of the displacement. They solved that, so we have to manage for solving that. In several cases, these three partial differential equations become quite simplified so as to being able for finding analytical solutions for that. And of course, in the process of integration, there will be some integration constants, okay? Whenever you have a partial differential equation and we integrate that, we have integration constants. So how do we solve the integration constants? Well, we have for them the boundary conditions. Look, the boundary conditions are expressed in terms of the displacements here, but this one is expressed in terms of the stresses. So since now they're unknown, we have reduced our problem to solve a problem in a space, in 3 dimensions, in terms of just 3 unknowns, the 3 components of the displacements. So we have just to express this boundary condition again in terms of the displacement. So we have to replace the stress here, so we have the boundary condition in terms of the strains, and then the strains here, the displacement, the gradient of the displacements here, and we have this equation in terms of the strain. So this is a formal action, more than this. So the boundary conditions can be just by replacing the stresses to the constitutive equation into here. We have that, and then we operate a little bit. So finally, we have this boundary condition in terms of the gradients of the displacement. So now we have a very easy task, a complete system. Now we have a system of equations, that system of equation, what are called the Navier equations. So the Cauchy's equations, when are rewritten in terms of the displacements, are termed Navier equations. Probably the name of Navier is familiar to you. Navier, the famous Navier that you know from equations of Navier in the strength of materials. A civil engineer, by the way. A civil engineer was the first that got these equations and tried to solve them for a number of cases. And then combined with the boundary conditions in terms of the displacements, provide the solution of the system. We are going to solve these equations, in fact. But even that these equations are simplified, are relatively very difficult to be solved in the general case, because there are 3 partial differential equations plus the boundary conditions and so on. We are going to solve that for educational purposes. We are going to solve those equations in a specific family of problems which are simplified. So they are sometimes not general problems, but good enough for simplifying the mathematical tooling so that we can solve the equations, right? So in order to do that, many times we have to use specific geometries which are simplified, where we can do several assumptions that simplify the problem. So these geometries are typically geometries that can be better represented in curvilinear coordinate systems, typical the cylindrical and the spherical system of coordinates. I mean, essentially nothing changes. The equations, these equations have a specific format in a specific curvilinear coordinate systems. So here we have the equations. We have also the equations in the form. Look, for cylindrical coordinates, cylindrical coordinates, we have the coordinate r, the coordinate theta, and the coordinate z. Okay? So in terms of that, the unknowns are the displacements, are the displacement ur, so the displacement in that radial direction, the displacement u theta, the displacement in the circumferential direction, and the displacement u theta, which is the displacement in the vertical dimension. Then, look that these equations are, you can recognize these equations comparing with us. So, for instance, the term lambda plus mu, it appears here, lambda plus 2g, g is the shear modulus. The term, look at the right-hand side, what do you have at the right-hand side? The accelerations, right? So you can recognize in these equations the accelerations at the right-hand side, okay? Expressed in terms of the time derivative of the components of the displacement. By the way, if we are told, or we assume that the problem is quasi-static, then what would happen with these terms? Zero, okay? So as soon as we are told, let's consider that quasi-static problems. Whatever is at the right-hand side of the quality, the term of accelerations automatically drops to zero, okay? And, well, you know that in order to compute these equations, they are written in such a structured way. Then first you compute the E. What is E, remember? E, what did we use the term E for denoting what? The volumetric strain, you remember? Volumetric strain. So this is the volumetric strain in cylindrical coordinates. Then this omega r, omega theta, omega z. What is that? These are the rotation angles. You remember the rotation angles that we talked about in the strain chapter. So you compute these, you compute that, then you replace everything in here, which is simplified in terms of that, and you solve these equations. Okay, and we'll see that in certain problems in spherical coordinates, in cylindrical coordinates, we can do a lot of reasonable assumptions from the scratch in order to simplify the equations, okay? You will see that. And the other situation in which we will work is in the spherical coordinates. You know, in the spherical coordinates system, when the geometry of the problem and the loading system keeps this spherical symmetry, then we work in spherical coordinates. You know that the coordinates are the radial coordinate, which is that one, the parallel coordinate, which is that one, and the azimuthal coordinate, which is that one. The meridian. So it's like looking at the Earth as a sphere. That would be parallels, and that would be meridians, right? So the components of the displacements at every point are in this local system x prime, I prime, z prime, which are locally attached to these three directions. So this gives rise to three components of the displacements: ur, the displacement in that directions; u theta, the displacement in that direction, sorry; and u phi, sorry, the direction in the component in this direction. So again, when working with that, the Navier equations taken a special format when developed component by component. Whenever you can recognize the term lambda plus 2 mu, here is the volumetric strain in spherical coordinates. We see here the rotation vector component r, theta, and phi, which are, I mean, in terms of the rotation tensor, certain components of the rotation tensor, it can be computed like that. And finally, again, you can see at the right-hand side the accelerations, which can be made zero whenever we make the assumption that the problem is quasi-static. Okay?